You ever wonder how we get from small, simple molecules to the huge, complex ones all around us? Well, a lot of the time, it comes down to this one really cool trick in the organic chemistry playbook. And today, we're going to dive right into the world of molecules called alkenes to see exactly how they pull it off.
So, the secret is, well, it's actually beautifully simple. You start with this thing called an alkene, right? It's just a molecule with a carbon-carbon double bond. Now, when you react it with something else, that double bond, it kind of pops open. And when it does, it creates two brand new spots for other atoms to latch on. We'll call them X and Y for now. And boom, just like that, you've added stuff to the molecule and made something totally new. This whole process, it's called an addition reaction. Okay, so what is the big deal with these alkenes? Why are they so special? Well, think of them like the ultimate chemical Lego bricks. And all their power, it comes from that carbon-carbon double bond. See, it's not just gluing two carbons together. It's an area that's super rich with electrons, which basically makes it a hotspot for chemical action. It's the perfect place to start building bigger things.
Now, this whole chemical dance, it really has two main players. First, you've got the alkene, which is, super generous with its electrons. It has plenty to share. And on the other side, you've got something called an electrophile. The name literally means electron lover. This guy is electron poor and is desperately looking for electrons. I mean, it's a classic case of opposites attract, right?
All right, so we've got our electron-rich alkene and our electron-hungry electrophile. The stage is set. Let's break down how this whole addition reaction actually happens, step by step.
It's a really neat two-step process. First up, step one, the attack. The alkene's rich double bond reaches out and grabs the electrophile. This creates this temporary, kind of unstable middleman, an intermediate with a positive charge. We call it a carbocation. Then comes step two, the payoff. Another particle, this one's called a nucleophile, a nucleus lover, sees that positive charge and is immediately drawn to it. It swoops in, forms a new bond, and bam, we get our final stable product.
Okay, that seems pretty straightforward, right? But you know chemistry. It always loves to throw a curveball. So what happens if the alkene isn't perfectly symmetrical? What if the two sides of the double bond are different? Suddenly, the reaction has a choice to make, and we have a puzzle on our hands.
And this is the big question. Let's say you're adding something like hydrogen chloride. It's got a hydrogen part and a chlorine part. Where do they go? Does the hydrogen attach to the carbon on the left or the one on the right? Does the chlorine go to the other one? I mean, does it even matter which way they add?
Well, it turns out it matters a lot. Chemists started noticing that these reactions aren't random at all. Nope. In fact, they're incredibly predictable. When the reaction is faced with two possible options, it almost always chooses just one single path. We have a fancy name for this, regiospecificity. It just means nature has a favorite, and that preference follows a very specific rule.
And here is that rule. It's called Markovnikov's rule. Seriously, this is like the ultimate cheat sheet for this kind of reaction. The easy way to remember it, the rich get richer. So when you look at the two carbons in the double bond, the hydrogen atom always goes to the carbon that already has more hydrogens attached to it. And the other piece, the X part, that just goes to the other carbon, the one with fewer hydrogens. Simple as that.
And look, this is not just some abstract rule you memorize for a test. This principle is an absolute industrial powerhouse. Get this, in the US alone, over 300,000 tons of ethanol are made every single year by, you guessed it, adding water to an alkene. That process is called hydration, and it follows these exact same principles. It just goes to show you how massive the real-world impact of this chemistry really is.
But why? Why does this rule work so perfectly? I mean, the rich get richer is a great way to remember it, but it's not a real scientific explanation, is it? Well, there's a much deeper, way more elegant reason hiding just under the surface, and it all boils down to one simple word: stability.
Okay, let's go back to that intermediate we talked about a minute ago, the carbocation. This is the key to cracking this whole thing. Remember, it's a flat, positively charged structure. It's got an empty spot just begging for electrons, which makes it super reactive and pretty unstable. But here's the secret. Not all carbocations are created equal.
And this is where you can really see the difference. It turns out, the more carbon groups you have attached to that positive carbon, the more stable the whole thing becomes. So why is that? Well, you can think of those neighboring groups as being like little electron clouds that help to shield and spread out that really uncomfortable positive charge. And here's a fundamental truth in chemistry. Nature always prefers the path of least resistance. It's always going to go down the path that forms the most stable intermediate.
So, there it is. Now we can see the real meaning behind Markovnikov's rule. It's not just a clever memory trick. It's a direct consequence of carbocation stability. The reaction is always going to favor the pathway that makes the most stable possible intermediate. The rule we use is just our handy way of describing this fundamental principle in action.
Okay, so now that we've got a handle on the core mechanism and the rule that runs the show, we can start to see just how incredibly versatile this reaction is. It's like a foundational tool in any chemist's toolbox, one that you can adapt in a ton of different ways.
And we're not just talking about adding a hydrogen and some other atom. By just changing up what you reacted with, chemists can do a whole range of different additions. You can add water, that's hydration, to make alcohols. You can add hydrogen, hydrogenation, to make things like oils into solid fats. Or you can add 2 halogen atoms in halogenation. The core principle is always the same. That double bond opens up. And that's what makes this such a powerful and flexible way to build new molecules.
But of course, just when you think you've got it all figured out, chemistry hits you with another layer, a new puzzle. So what happens when a molecule has more than one double bond? What if they're neighbors, right next to each other? Do they just do their own thing, acting independently, or do they influence each other?
Well, this brings us to a really special class of molecules called conjugated dienes. And they have this very specific pattern. It goes double bond, then a single bond, then another double bond. The setup is no accident. It's a special arrangement that actually allows the 2 double bonds to talk to each other electronically.
And the reason they can talk is pretty cool. The electron clouds that sit above and below the bonds, they can actually overlap across that single bond in the middle. So instead of having 2 separate, isolated double bonds, you get this one continuous electronic highway that runs along all 4 of those carbon atoms. The molecule totally stops behaving like 2 separate alkenes and acts like one single interconnected unit with its own brand new set of rules.
And that really leaves us with a final thought, doesn't it? We started with what looked like a simple addition reaction, and we uncovered this hidden rule of stability that was secretly running the whole show. But then we found out that even those rules can change when molecules have these hidden connections between their bonds. It just makes you wonder, in this huge, elegant world of chemistry, what other hidden connections, what other deep principles are just sitting there, waiting for us to discover them?